This problem is a little more involved than some of the other big picture problems we've done. As you can see here, the box is going to slide down a curved track. There's no friction. It starts 3 meters above the ground, but when it runs into some level ground, then it does encounter some friction right in here. And then after slowing down some, it then is going to slide up this ramp of 30 degrees. And the question is, how far up the ramp does it slide? So the question is not asking to what new height it's sliding, but to just literally how far up the ramp. So a lot of things going on here, but we're going to find out as long as you approach it from an energy perspective. What looks complicated really isn't. We're just going to run through our questions as always. All right, so let's start with our objects. We have the box and the track and the earth, and so there's a weight force and there's a normal force from the track. So maybe that was actually somewhat of a waste of time, though this up here was not. Okay, so let's just run through our questions. Was there a change in speed? Well, it started at rest and it ends at rest, so no change in speed. Was there a change in height? Yes, there certainly was a change in height. There was no spring involved, but there was some work being done by friction. And of course I put that as a negative sign, because for us friction will always take away energy, making it negative work. Alright, so we have mghf minus mghi equals the negative force of friction D. Now the final height we don't know, but we do know the initial height is 3. So this is mg hf minus 3. So I did a little factoring there. Equals negative 0.3 mu times m times g times d. Because this looks pretty simple, because it looks like both the mass and the strength of gravity come out. And so now I have hf minus 3 equals negative 0.3 d, but d is 1 from the problem, so hf minus 3 is negative 0.3, so hf is 2.7 meters. Now that's not the answer. That is to the new height at which the box rises, and you notice it is less than 3. That makes sense because some of the energy was taken away by the work done by friction. But actually we need to figure out how far up the ramp it goes. This is old stuff for us. We have a triangle. That's a pitiful triangle, but okay. We know this is 30 degrees, and we now just figured out this is 2.7. So the question is, how far up the ramp did it go? And since it's involving the opposite edge and the hypotenuse, this is a sine function. So the sine of 30 would be 2.7 over the distance up the ramp. And so the distance up the ramp is 2.7 divided by the sine of 30, and that works out to be 5.4 meters. So it's a long ramp. It has to be. If the ramp had been any shorter than 5.4 meters long, then obviously it would have just gone off the end. So it looked kind of troubling because there was a curved section at the beginning and a little friction in the middle, and then it had a ramp on the end. But if you see, really, from looking at it from an energy perspective, it was a very simple problem. It was just there was a change in potential energy to gravity, but at the same time, work from friction was taking away energy, and turned out to be a quite simple problem to solve.